So, hi, I'm Brody. I'm a planetary science major here at Purdue, and I'm going to be talking about the solar system. So, we're going to take a tour through the solar system. If you have any questions, feel free to raise your hand, and I can call on you, or go ahead and post anything in the chat. I have that pulled up as well. Your questions are very important. First, let's start off with a question. What patterns, similarities, and differences do you observe in the planets of the solar system? So here I have, the 8 planets plus a few more. What are some patterns that you observe?
Something that I see is that the outside ends are smaller planets than the middle.
Yeah, that's really good. That's great, Greta. Yeah, you'll notice that the small planets are located on the inside of the solar system and the outside of the solar system. So what does that mean for the middle, Jack?
I was gonna say that the first planets are just made of rock, and the ones farther back are colder and made of gas.
Really, really good, Jack. Yeah, that's really good. So these inner planets are what we call terrestrial planets in planetary science, or you can call them rocky planets too. And that means that tells us something about their composition. Can someone, and Jack, I think you also mentioned that the outer planets are made of gas, and that's true. We call these middle planets gas giants, specifically Jupiter and Saturn. Does somebody know what we call Uranus and Neptune?
Don't you call them blue giants?
That's really good, Kendall. The blue, so we don't call them blue giants. That's not right. But their color is blue, and it tells us something about their composition and what they're made of. So we call these planets the ice giants because they have a blue tint to them, and their compositions are made of ices like water ice and methane ice. So these big planets together make up what we call the giant planets. So can somebody tell me what the remaining planets are called?
Dwarf planets.
Yeah, really, really great, Logan. They're called dwarf planets. And so together, these four categories make up all of the planets that we see in the solar system. So we have a poll for you. Poll number 1 should be able to bring it up here. Dave, do you have it? Alrighty, let's go ahead and move on. So most of you seem to put all of the above, and we have a few choosing the answer A. So the answer is indeed all of the above. So the way that the giant planets form and get so large is that they had access to more matter, gas, and dust during their formation. They also had access to these ices that we've been mentioning, and they consumed a lot of other tiny planets during their formation. So if we can close this poll here. So why are the giant planets so large compared to the size of the other planets? So here I have a diagram that shows the 8 planets, but there's something separating these eight planets. So can someone?
The asteroid belt?
Right. So the asteroid belt is, I didn't quite catch who said that, but the asteroid belt lies on the inside of something that's very important in this diagram, because it's made of mostly rock and metal. So can somebody tell me briefly what is separating the inner planets from the outer planets in this diagram?
The ice line.
Yeah, Logan, the ice line. And the ice line is very important because it sets a marker in our solar system where ices and more material will be present. And so in the diagram here, we see that the ice line separates the part of the solar system that has solid ices from the part of the solar system that doesn't. But you'll also notice that rock and metal is throughout all of the solar system, that all of these planets have access to rock and metal. Can anyone tell me why the solid ice wedge and the rock metal wedge get smaller as you go out?
Because it gets colder. The farther you go away from the sun, it gets colder.
Yeah, that's right. Yeah, it gets colder. That's certainly a big factor. We're losing the sun's heat as we move farther away from the sun, which is why we get more ices in the middle. But all of these, all solid ice and rock and metal disappear in the solar system because the sun's gravity is pulling everything closer to it. So we have what we refer to less mass out in the solar system. I think somebody mentioned that the smaller planets seem to be contained on the inside and the outside. And this is why Pluto and Eris, those dwarf planets, are so small, because they have access to less material, and the wedges show that. So here are I'm going to show you some interior slices of the rocky or terrestrial planets and the gas giants. So first, let me show you the rocky planets. Should be able to see that pop up on your screen here. And a few questions for you all, really quickly. What do we think molten rock is in this diagram? Does somebody know what molten rock is?
Lava.
Lava is a good
Magma.
Oh, that's even better, right? So magma is molten rock, or rock that is close to liquid, not quite like water, but you can think about it like silly putty. And this is magma when it's inside of the earth. But Logan, we call this lava when it's outside of the earth, like what would happen during a volcanic eruption or something like that. So we can see that most of the inner planets are contained of this molten rock. Some have more of it than others. But it's very important in terms of how these planets formed. It tells us something about their formation. Does anyone know what a solid and liquid metal is? What's the difference between those? Or why they are where they're at in the diagram?
Because the closer to the core you get, the hotter it is, and then stuff gets hot and there's a lot of pressure.
Yeah, Logan, you nailed it right there. It all has to do with heat, temperature, how hot things are, and pressure. So in between this section of molten rock and solid metal, like iron starts to become liquefied because of the temperature and pressure of that region. And then it begins to solidify because all of the weight of the planets are compacting the metal in, which is why we have solid and liquid metal in most of the rocky planets. So I want to contrast this with another image, that of the gas giants. Let's get maybe someone we haven't heard from in a little bit. Lyle, would you be able to tell me what you think is the main difference between the gas giants and the rocky planets?
There is gas in the gas giants, and there is no gas in the rocky planets. They have metal, solid rock in the rocky planets, and only a little bit at the core of the gas giants.
Yeah, that's right. So if we can think back to our diagram, previously, we can start to see the effects of the ice line in the composition of the planets and why the outer ones are so much bigger, because they had access to this material, these ices, and more of this gas to build these very large atmospheres. And so we can see Earth located right here. Okay, this is the actual Earth size compared to the gas giants and the ice giants. So they have a lot of liquid hydrogen, which it's so cold out there, right? What is hydrogen usually? What state of matter is hydrogen usually on our planet?
Gas.
Good, Logan. Yeah, it's a gas, and we see that some of these planets have gaseous hydrogen. But out there, it gets so cold that hydrogen starts to become a liquid.
Hey, Brody.
Yeah.
I've got a question. Something came up in the chat, and that is, why do we always talk about hydrogen? You know, hydrogen in the planets and hydrogen. Why aren't other gases present?
No, this is a very good question. Hydrogen makes up a majority of the matter that we can see in space. Hydrogen is so plentiful and is always, it's the simplest atom to make, hydrogen. It's one proton and one electron. So it's a very simple compound, and it's spread all throughout the universe. So we usually talk about, when we see a lot of hydrogen, there's usually a lot of other gases as well, but hydrogen makes up the bulk majority because it's easy to make. The universe has a lot of it. So can somebody tell me what they think metallic hydrogen is?
Solidified hydrogen.
Yeah, Logan. Yeah, that's really good. It's hydrogen that, again, due to these temperature and pressures, kind of what we see why we get liquid metal in some of the rocky planets. We get this metallic hydrogen because the pressure and temperature is squeezing the hydrogen so much that it starts to have a lot of metallic properties, kind of what we see here on metal here on Earth. So it's an interesting product of how big the giant planets are and where they're located. So let's go ahead and ask you another poll to kind of get your brain juices flowing here for the next part. So we'll give you guys some time here to answer this question. Think carefully, but no wrong answers. We're all gonna learn together. So we'll give you maybe another minute to look it over, make your final choices. Okay, so it looks like a majority of you chose C, and we have the next one being A, and the lowest is B. So the answer for this question about early solar system formation is all of them. So all of them are correct if you chose all of them. During the early formation of the solar system, masses were exchanged between the planets. They moved closer and further from the sun multiple times, and they formed at different times. The solar system is very old, 4.5 billion years. Throughout that time, we had a lot of different things coming and going from the solar system. So here I'm showing you a simulation, which is really a computer model that a scientist used to try and understand something of our early solar system. I want to just point out very briefly that the red areas that you see have really high mass, and the blue areas have little to no mass, while the green areas have some mass, but not as much as the red. And really what the simulation is doing is referring to what we call density. So, someone go ahead and shout out what you think your observations are of this simulation.
The closer,
what do you see?
The closer inward you get to the planet, the more dense it is.
Yeah, really good. You said planet. Does somebody, can you elaborate on that for, what do you mean by planet? Where is the planet in this simulation?
I think the planets are the little red dots and the big dot. I think the big dot's the sun and the littler dots are the planets revolving around it.
Yeah, that's really good. Really good. In a way, that's exactly what's going on here. I noticed that, Lyle, you said that it looks like a tornado swirling around. And that's also another good observation. In the early formation of the solar system, you had a lot of motion in one direction, which is why all the planets move in the solar system in one direction, because the gas that they were born from and the mass from the solar system all started to move in one direction. So here at the start, we see some areas becoming attracted to one another. What attracts the red mass to each other?
Gravity.
Good, gravity. Right. So every body, okay, even you and me, have gravity. We exert a gravitational force on each other. And the planets do the same thing when they were forming. Has anyone counted? How many planets do you see from this simulation? No, maybe let's get someone we haven't heard from.
I see 6.
Good, 6, yeah. What about right there? How many do we think was just in that part of the simulation?
9.
Yeah, right. So we're getting a lot of planets forming, and then we're moving from areas where we have, upwards of 9, maybe 10 planets down to 6 and some more. So our solar system didn't necessarily have to have 8 planets. At some point, it had a lot of them. I just also want to point out that this is what's known as a heat map or false color simulation. None of these colors are real. The planets aren't really red, and space isn't really blue. But scientists color simulations like this to show things like how dense or how massive certain things are. Let's get someone, let me call on someone here. Jack, why does the center of this simulation remain red?
Because it's the sun.
Yeah, that's right. So the sun is at the center. What's the sun doing to this material?
It's spreading it out.
That's right. Yeah. So the sun is, its gravitational force is attracting the planets, and they're moving. So it's kind of like being on a playground, right? And spinning on the carousel, and you feel, or going around a bend in a car, right? And you kind of feel pulled outwards. The motion that the plants are in spreads them out, but the sun is pulling a lot of this material inwards towards itself and consuming it, right? So just as we see the planets pulling material in, the sun does this. So let's go ahead and move to another poll. So this question is about Earth's water. Where did all this water come from? We saw previously that the ice line is outside of Earth. And so water wasn't able to form inside of the ice line, because when the sun ignited and turned on and started shining, it heated up the inner part of the solar system, and water wasn't able to form. So where do we think the water came from? Give you a few more moments to think about it. Okay, let's go ahead and make your final answers. And so it looks like, a nice 50-50 split between B and C. Yeah, so, so good. Nobody chose A. So the answer is C, and nobody chose A. That's right. So water didn't flow out of the inside of the planet or outside of the rocks. It was just rock and metal that formed Earth. And it wasn't B either. So at the early in Earth's formation, we had a different atmosphere, right? We had an atmosphere of hydrogen and helium, similar to the giant planets. But when the sun was shining very brightly at the beginning of its lifetime, it blew away a lot of Earth's early atmosphere. So our water didn't come from our atmosphere. In fact, our atmosphere has changed a lot. The answer is C. A majority of our water came from the outer solar system and was delivered to us by comets. So we had bodies that formed outside of the ice line and delivered it. So here I'm showing you a diagram, and it might look complicated at first, but don't worry, it's not too difficult. So what we see here is a dot simulation or a dot model of our solar system, with the sun being on the left, and here we have our rocky asteroids. Okay, what's missing from this first part? We see rocky asteroids, but what are we missing from the inside here?
Our terrestrial planets.
That's right, Drac. Very good. So our terrestrial planets at the very start of our solar system had not formed yet. Okay. However, we see Jupiter, Saturn, Uranus, and Neptune. They're already formed at the start of the solar system. They formed very, very early. So the ice line kind of sits right here between the rocky asteroids and Jupiter. And here we have icy asteroids that contain water ice, since they're outside of this ice line. And if we look down, what's happened 70,000 years after the start of the solar system? What's happened to the position of the planets? Somebody, yep, go ahead.
The position of the planets between Jupiter and Saturn, they moved closer together, and then Uranus and Neptune basically stayed where they were, and the rocky asteroids basically stayed where they were, and the icy asteroids kind of moved forward with Jupiter and Saturn.
Yeah, really good, Greta. Nailed it right on the head. That's for sure. So Jupiter, we know, moved inwards towards the sun sometime in the early solar system. And in doing so, it bunched up a lot of the rocky asteroids together. And if we can remember back to our computer model, our simulation, this would be like having a lot of material contained in one small area or volume. And in doing so, Jupiter has cleared a lot of its lane and pushed Saturn a little more forward. Can somebody tell me what's happened from the position of the planets at 100,000 years? What's happened here? What's different from the third panel from the first two?
Saturn and Jupiter are touching each other, probably due to their strong gravitational forces.
Yeah, really good, Jack. So we have Saturn and Jupiter. So Jupiter exerts a force on Saturn, and Saturn responds. It says, okay, I'll come in and hang out with Jupiter. What we also see is because the giant planets, right, Jupiter and Saturn, are so much bigger than the others, they have brought with them icy asteroids and put that inside of the rocky asteroids. I'll just briefly go through the rest of it. After the giant planets moved in, they then proceeded to migrate back out. And in doing so, caused a whole bunch of material, rocky asteroids to go out into the end of the solar system here, and icy asteroids to come inside to the inner solar system. We start to see a lot of these circles get bigger, right? And that's to represent a lot of these rocky asteroids forming our inner terrestrial planets. As the giant planets start to migrate back out, if we look here at 600,000 years, where did Uranus and Neptune go? Where did our ice giants go in this picture, in the final at 600,000 years?
Way back that you can't even see them in the graph.
Good, Jack. Yeah. So Jupiter and Uranus and Neptune are hanging out right here at the end. And we see Jupiter and Saturn in their where we can observe them today. But notice here that we have some icy asteroids inside of the ice line now, and that Earth has a nice little ring of water surrounding it. Because when Jupiter and Saturn moved into the early solar system and then moved back out, they took water ice from the outside and put it in the inner solar system. So this was something that is very important for why we have so much liquid water here on Earth. So what, if anything, do you think lies beyond the orbit of Neptune? You can just, shout it out or put it in the chat.
More asteroids.
Yeah. Anyone else? Any other dissenting opinions? Good. Lyle, yeah, a lot of icy asteroids and dwarf planets, Loretta, Jack. Yeah, very, very good. Very good. So if we look here, there's really two things that lie beyond the orbit of Neptune. We call this the Kuiper Belt, which is where Pluto and a lot of those dwarf planets that we saw at the beginning of this slideshow, where a lot of them orbit the sun. And then far, far beyond, if we really look in here, our sun is at the center of our solar system, right? It's just a little tiny dot in the middle of that donut in what we call the Oort Cloud. And the Oort Cloud is this giant sphere of icy bodies and icy asteroids that orbit the sun from way out, that our solar system is just inside of that tiny little donut. Okay, so I'll ask the question, does anyone think anything else is out there beyond the sun besides the Kuiper Belt and the Oort Cloud?
Other solar systems?
Yeah, really good. Other solar systems, specifically other planets, right? So you might not even have to go to another solar system to find another planet. We might not have found them all. And this is something to kind of leave off on, that there's still a lot left to discover. Some scientists think that a Neptune-sized planet, what this is referring to as Planet 9, is orbiting our solar system far beyond the orbit of Pluto and the giant planets. And we see evidence of this in this diagram by having a whole bunch of these other icy comets bunched up. So we think that given their orbital positions in the outer solar system, that there might be something here that we just haven't found yet. So this is a hotly debated topic in the planetary science community, whether there's another big Neptune-sized planet far beyond the asteroids. So that's the end of my presentation. I'll go back here and stop sharing my screen. If you have any more questions about the early solar system, feel free to put something in the chat. Feel free to put something in the chat, or shout out a question and we'll try and answer it. So thanks everyone. This was a lot of fun. I'll hand it back to Dave.
Brody, before we let you go, I'm going to ask you one question. I want a short, succinct, 30-second answer. Where did you develop an interest in planetary science?
Yeah, I think it started here at Purdue. I was in physics for my first degree, and I wanted a little bit more out of my education, so I decided to go across the hall here to planetary science, and it kind of all started here at Purdue. So